Welcome. This video is going to start looking at the gas laws, and we're going to start with the simplest gas laws known as the individual gas laws. And because we're constantly surrounded by air, most of us know quite a bit about the individual gas laws already. And the individual gas laws are the simplest gas laws because they only look at two of the four variables at a time. So one variable is changed, effect on another variable is measured, while the remaining two variables are held constant or not allowed to change. And the four variables that affect gases are pressure, volume, temperature, and then the number of moles, which is really just a way of counting the number of gas particles. So some everyday examples to show you that you really do notice this every day is if you squeeze a balloon, another part of that balloon is going to bulge out. If you take a basketball out into the cold, it's not going to bounce very well. And if you take a balloon out into the cold, you would expect it to shrivel up or look like it's losing air. So if we look closer at what's actually going on in each of these cases, in the case of the balloon, if you squeeze a balloon, you're decreasing the volume, and you see the bulge because the pressure is increasing in other areas of the balloon. With the basketball, you're decreasing the temperature, and that's also going to decrease the pressure, which is not going to allow it to bounce very well. In the case of the balloon, when you decrease the temperature, we can physically see the volume decrease as well. So these three examples represent the three individual gas laws. So we'll look at them one at a time. The first is called Boyle's law, and Boyle's law looks at the relation between pressure and volume. So volume is just the size of your container or the space your gas is taking up, and since gases will take up as much space as you give them, when we're dealing with the gas laws, it's assuming the gas is in some kind of container that you're limiting the volume. And that container may be able to expand like a balloon, or it may be what we call a fixed container, something solid like your water bottle with the cover on. Pressure is determined by the number and speed of collisions that the gas particles are having against the side of the container specifically, as well as each other. So more collisions is going to be more pressure. And faster collisions is also going to lead to greater pressure. So logically, more space should decrease collisions, right? If you have bigger hallways, more space, fewer people bumping into each other. Well, less space will increase collisions. Narrower hallways, more bumping and jostling. So this is known as an inverse relationship. When one variable increases, the other variable will decrease. It's expressed as P1 times V1 equals P2 times V2. And that means if you take your original pressure and volume and multiply them together, it has to give you the same number as your second pressure and volume. And you can see if you look at this mathematically, if you plug some numbers in, if P1 goes up, then V1 has to decrease in order to get that same product. And the other thing is it's assuming the temperature and the number of moles is remaining the same. The other two variables are staying constant. So let's look at a quick example here. So my example says a diver blows an air bubble, 0.75 liters, and liters you should recognize as being volume, so that's the first volume that's being mentioned, so I'm going to put a V1. As the bubble rises to the surface, the pressure goes from 2.25 atmospheres, so that's the original pressure, P1, to 1.03 atmospheres, that's P2. What will be the volume of the bubble at the surface? So that would be my second volume. So I've been given P1, P2, and V1, and I'm being asked to find V2. So remembering that my equation is P1 times V1 equals P2 times V2, I'm just going to plug and chug here. So 2.25, and you can either carry your units with you now, your labels, or I know a lot of you just wait till the end, and that's fine, times 0.75 liters equals 1.03 atmospheres times our unknown, or V2. So I just have to get V2 isolated or by itself. So since I'm multiplying by the 1.03, I simply divide both sides by the 1.03. And I should come up with the value of V2, so I'm going to go ahead and plug this into my calculator. And as I'm plugging this in, I like to think about what logically should be happening. My pressure's decreasing, so if there's fewer collisions, that would indicate the volume should be bigger. And when I plug this in, I come up with an answer of 1.64, and my label then has to match the label of the original volume, which was liters, so that would be 1.64 liters. So my volume did increase, just like I would anticipate. The second individual gas law looks at the relationship between temperature and volume, and this is known as Charles' law. And on an atomic level, remember, temperature is how fast gas particles are moving. And when they're moving faster, they're going to collide more often, and they're going to collide with more energy. So logically, if gas particles have more energy, it should end up spreading or increasing your volume, because think of it like throwing a tennis ball against a wall. If you throw that tennis ball with more energy, it's going to bounce further back. Just like gas particles colliding against the walls of the container with more energy are going to bounce further back. So if it's an expandable container, something flexible, it is going to expand and get bigger. This is a direct relationship. When one variable increases, making the other variable increase as well. Charles' law is expressed as V1 over T1 equals V2 over T2, because when one increases, the other increases. And it assumes that the pressure and the number of gas particles or moles is remaining the same or constant. So it's only volume and temperature we're dealing with. Like in this example, a helium balloon in a closed car occupies a volume, so there's V1. At 40 degrees Celsius, there's T1. If the temperature in the car rises to 75 degrees, there's T2. Well, the pressure remains constant. What's the new volume? So I'm being asked for V2. And just a quick note here, when you're doing these with your textbook, obviously you can't be writing in your textbook, or you shouldn't be writing in your textbook. So a lot of times I just make a chart over here. As I see the numbers, I just write down, okay, that's a volume, 232 liters. There's a temperature, 40 degrees Celsius. There's a second temperature, 75 degrees Celsius. And V2 is what I'm being asked for. Now, temperature brings up a whole new issue, because with temperature, as we'll look at in a lab, Celsius degrees doesn't really work for us because of the whole negative thing. You really can't have a negative temperature if temperature is measuring how fast particles are moving. How do you move negatively? When you reach zero, that's it. That's as slow as you can go, is not moving. So negative temperature really isn't a possibility. But of course, folks didn't know that way back 200-300 years ago when they were setting up temperature scales. So even though Celsius is very convenient because water freezes at 0 degrees, water boils at 100, it doesn't work so well for the gas law. So we have to use a new temperature scale called Kelvin. If you've heard of absolute zero, he's the guy who came up with the concept of absolute zero. So to get from Celsius to Kelvin, you simply add 273 degrees. And we'll talk about this more in class with the lab we're going to do. But that would mean I'm really dealing with the temperature of 313 Kelvin. Or with the 75, that's going to be 814, looks like 348 Kelvin. So now when I plug into my equation, V1 over T1 equals V2 over T2, this is going to be 2.32 liters. Just put a line here so you can see where my work is. 2.32 liters over 313 Kelvin is equal to, don't know how many liters, over 348 Kelvin. So now you cross multiply and divide. So I'm going to end up with the 2.32 times 348 equals 313 times x, or my unknown. So I cross multiplied. Now I divide by that 313. If I slide this up so I have a little more room here to finish up. Again, I think it's good practice to think about what should be happening. If my temperature is increasing, since this is a direct relationship, I should see an increase in my volume as well. And when I plug the numbers in here, I do see an increase in volume to 258. And again, it has to match my original label for volume. So 2.58 liters. So let's look gas law, which is Gay-Lussac's law, and it looks at the relationship between temperature and pressure. Again, remember, temperature is how fast the gas particles are moving, while pressure is the number of collisions. So logically, if gas particles have more energy, we would expect them to collide more often. So again, this is a direct relationship. One variable increases, the other increases as well. So this will also be expressed as P1 over T1 equals P2 over T2, and it assumes the volume and number of gas particles is remaining the same or constant. So if we look at an example of this law, the pressure of oxygen gas inside a canister, so P1 is 5 atmospheres. And the 0.00 isn't so important. It just lets us know what our sig figs are for rounding at the end. At 25 degrees, that's Celsius, so right away I'm going to add the 273 on so I don't forget to. So really 298 Kelvin. Temperature falls, so my T2 excuse me, it falls to minus 10. And make sure you read carefully. Does it say it falls by 10 degrees where I'd have to subtract it? It says it falls to minus 10, so that is my new temperature. So plus 273 is going to be 263 Kelvin. What's the new pressure? So again, I've got P1 over T1 has to be equal to P2 over T2. As I plug in, I started at 5 atmospheres over 298, and my temperature fell. So because it's a direct relationship, I would expect my pressure to fall also. So when I cross multiply, 5 times 263 equals, and I shouldn't use the x there because that's sometimes misleading. How about if I use a dot like your mathematicians do? 5 times 263 equals 298 times x, so then I divide both sides by the 298, and if I plug that in, I would expect to see a decrease in my pressure as well.